Welcome to Circuit Masterclass, your go-to channel for everything in power systems, transmission, and distribution engineering. Don't forget to check out circuitmasterclass.com for in-depth blogs and bonus content. We have provided the website link below in the description. Let's get started. We are going to discuss the details of the control circuit of a high-voltage circuit breaker. We have considered here an SF6 circuit breaker. The control supply of a circuit breaker is always a DC supply. This is called selective DC supply. This type of supply is applied in higher voltage circuit breakers, 132 kilovolts and above. It is not for general purpose, but is a typical design used by some renowned circuit breaker manufacturers. Here you see, this is supply 1. Now this supply 1 is not supplying any voltage, meaning supply 1 is dead. If supply 1 is dead, the contactor K12, which is connected across the terminals of supply 1, is also de-energized. This K12 contactor is actually the auxiliary contactor for DC supply monitoring. As it is de-energized, the NO, normally open contacts remain open, and the NC, normally closed contacts of K12 remain closed. So when DC supply 1 fails, DC supply 2 will be connected to the circuit through this path. This is the positive path and this is the negative path. Now suppose DC supply 1 recovers. Whenever supply 1 is normalized, the K12 contactor gets energized. As a result, its NO contacts will close. DC supply 1 will now be directly connected to the control circuit. This is the main line of the control circuit. At the same time, as these 4 contacts are mechanically coupled, whenever these 2 normally open contacts close, the normally closed contacts will open. As a result, DC supply 2 will no longer be available to the circuit, provided the main DC supply 1 is in normal condition. But whenever the main DC supply fails, the supply will automatically change over to DC supply 2 through the function of these normally open and normally closed contacts. Hope you got the idea. Some manufacturers provide fuses in the positive supply line of both supplies and links in the negative supply line of both supplies to provide better protection for the DC supplies. But some manufacturers do not recommend providing any fuse at the entry point of the circuit breaker supplies, because if any of these fuses blow, it may cause an interruption of the DC supply. So there is no need to provide them, since DC fuses are already provided at the supply point from where the supplies come to the circuit breaker. So, an additional fuse and link unit may not be required here. Another difficulty is that providing a fuse here means introducing more chances of fuse blowing. There are generally 2 schemes. Some manufacturers and utilities prefer that the DC signal of the circuit breaker be sent to the control panel, and from that control panel, the normally open NO contact of a relay or switch comes back to the tripping circuit of the circuit breaker, so that whenever the relay contact or control switch contact closes, DC will go to the control panel and return to trip the circuit breaker. Some manufacturers prefer not to use this local DC for the tripping purpose of the circuit breaker. In this case, the DC signal or DC pulse for tripping should come directly from the control panel itself. So in that case, even if the fuses here blow, the circuit breaker can still be tripped, since the trip DC is coming directly from the control panel and not from this local supply. We should not provide any fuse in the negative path of this control circuit, because in the second scheme, the positive path comes from the control panel, but the negative path is common. If we provide fuses here in the negative path and these fuses blow, then even if the DC comes from the control panel, due to the discontinuity in the negative path, the breaker will not open. To overcome this difficulty, manufacturers normally do not provide a fuse in the negative path. Instead, they provide a link so that for maintenance purposes, the link can be removed to isolate the DC supply from the source. That is the only purpose of the links in the negative path, isolating the negative path for maintenance purposes. Some manufacturers provide fuses at both connections of the auxiliary contactor, 1 fuse here, another fuse there. This is because if, for any reason, this coil gets shorted. Then either of these fuses will blow and save the rest of the circuit from the effects of the coil's short circuit. This is considered a good practice. This is the trip circuit. Now we will enter into that white block which we have labeled as the trip circuit. We will now look into the detailed circuitry of this block. Here, you can see the trip coil. This contact is a normally open NO contact of the auxiliary switch of the circuit breaker. And this is the normally closed NC contact of the auxiliary switch of the circuit breaker. So when the circuit breaker is in the open condition, this switch will be in the open position, and this switch will be in the closed position. This is the SF6 lockout contact. When the SF6 gas pressure is normal or above the trip limit, this contact will remain in the closed position. And when the circuit breaker is in the closed condition, that switch NO will be closed and the NC contact will be open. Now this is the local remote switch. Currently, the switch is set to remote, so you can operate the circuit breaker from the control room. If it is set to the local side, then by pressing this push button or rotating the associated tripping switch, the DC voltage, meaning local DC voltage, will come to the tripping coil following this path. Since the SF6 gas is at normal pressure, that contact will be closed, allowing the negative potential to reach the coil terminal. As a result, the coil will be energized and it will trip the circuit breaker. What's your understanding here? From the tripping circuit, we can clearly see that there are two conditions to be fulfilled for tripping of the circuit breaker. One is that the circuit breaker must be in the closed position. If the circuit breaker is in the closed position, then only this auxiliary switch contact of the circuit breaker will also be in the closed position. This NO, normally open, contact of the auxiliary switch of the circuit breaker is in a closed condition. And if the pressure of the SF6 gas in the circuit breaker is above the lockout pressure, then the SF6 lockout contact will also be in the closed position. If these two contacts are in the closed position, and the local remote switch is in local position, then only by pressing the local trip push button, we can trip the circuit breaker. This is the pre-closed supervision terminal, which means when the circuit breaker is in the open condition, then through this path, the pre-closed supervision indication on the control panel is connected. Because when the circuit breaker is in the open condition, these auxiliary contacts will be in the closed condition. This is the post-close supervision, because after closing the circuit breaker, this contact will be in the open condition. So this path will not give the supervision signal because it will be open. In that case, we will get the signal from this path. Now come to the closing circuit. This is the positive line of the DC supply. From here, a branch comes down and connects to a contact of a push button or a rotating switch. If the contact of that push button or rotating switch is made, then this voltage will flow further. The positive voltage then reaches the local terminal of the local/remote switch. Now, if the switch is selected to local, the positive voltage continues to the closing coil via several contacts. These include a normally closed NC contact of the anti-pumping relay, a normally open NO contact of the SF6 general lockout relay, a normally closed contact of the auxiliary switch of the circuit breaker, a normally closed contact of the spring charging mechanism. When the circuit breaker is in the open condition and the spring is fully charged, only then can the circuit breaker be closed. Let us now examine the condition of the contacts drawn in series with the closing coil. If the SF6 gas pressure in the circuit breaker is normal, above the lockout pressure, then the SF6 general lockout contact will be in the closed position. The anti-pumping relay's contact will also be closed because the relay is inactive before switching on the circuit breaker. Since the circuit breaker is in the open condition, the normally closed auxiliary contact is also in the closed position. So when we operate the local closing switch, voltage appears across the closing coil via this path, and the closing operation is initiated. Once the breaker is closed, the normally closed auxiliary contact, which is in series with the closing coil, opens, and the normally open auxiliary contact, connected in series with the anti-pumping relay coil, closes. As a result, the anti-pumping relay gets energized. When this happens, the normally open anti-pumping relay contact closes. The normally closed anti-pumping relay contact opens. This breaks the closing circuit, so even if the closing switch is still held down, no further closing pulse is applied. This is the function of the anti-pumping relay. Otherwise, in the case of a faulted line, if the breaker is closed, it will trip immediately. But if someone mistakenly keeps holding the switch, the breaker would close again and again. To prevent this unintentional reclosing, the anti-pumping relay is provided. Now we will see how the remote closing operation is performed in this control circuit. Whenever we rotate the rotary switch of the TNC switch, trip neutral close switch, or press the push button provided for closing operation in the control panel, and if the local remote selector switch is set to the remote position, then a positive pulse from the control room will reach the closing coil. In the closing operation, it is also possible for the local DC supply to be sent to the control panel and then return to the closing coil through the contact of the closing switch. However, it is a common practice to close the circuit breaker using the positive voltage from the remote control panel. In our scheme, we are using the positive voltage from the remote control panel to close the circuit breaker. The operation remains the same as in the case of local operation, where the selector switch is set to the local position. Here, instead of providing DC voltage directly from the breaker side, the DC signal required for closing is supplied from the control panel, and this signal reaches the closing coil through the local remote selector switch. Auto recloser terminal from the control panel is connected after the local remote switch. The auto reclosing of the circuit breaker effectively bypasses the local remote selector switch. Now we come to the supporting circuits of a circuit breaker. Among these, the trip circuit and the closing circuit are considered the main control circuits. The rest of the circuits are auxiliary in nature, meaning they support the main operation of the breaker in various ways. These auxiliary circuits handle a number of important tasks. For instance, they provide on-off indication, spring charging status, an operation counter to track how many times the breaker has operated, real-time information on whether the spring is charged, charging, or uncharged, and SF6 gas density monitoring to check whether the gas pressure is normal, at an alarm level, or in lockout condition. All of these features require additional wiring and dedicated circuits within the control system. Let's take a closer look at how this works. In the control circuit, there's a counter that connects through a normally open contact, also called an NO contact, of the main auxiliary switch. When the circuit breaker turns on, this NO contact closes and the counter increments by 1. This way, we can keep track of how many closing operations the breaker has completed. There's also a normally closed contact, or NC contact, from the same auxiliary switch, which is often referred to as ISH1. This contact stays closed when the breaker is in the off condition. During that time, a green lamp glows to indicate that the breaker is open. Now, when the breaker switches on, another NO contact closes, causing a red lamp to glow. This tells us the breaker is in the on condition. The green dotted lines you may see in circuit diagrams typically show that all these auxiliary contacts are mechanically linked. Let's move on to the spring charge indication circuit. A limit switch is installed in the spring charging motor. When the spring is uncharged or in a relaxed state, this limit switch changes position, allowing power to flow to a relay coil. When the coil gets energized, it causes the spring charging contact to open. Now, once the spring becomes fully charged, the limit switch returns to its original position. This cuts off power to the relay coil, which then de-energizes. As a result, the spring charging contact closes and a blue lamp turns on to show that the spring is now fully charged. This setup also serves an important interlocking function. The closing operation cannot proceed unless the spring is completely charged. That's because a contact from the relay coil is connected in series with the closing coil. So if the spring isn't charged, the breaker simply won't close, protecting it from mechanical issues or incomplete operations. Finally, Let's look at the SF6 gas density monitoring system. There are two types of density monitors used here. One triggers an alarm, and the other triggers a lockout. The position of the density monitor swing is such that there is no sulfur hexafluoride gas inside the breaker. Now, when we fill the breaker with sufficient SF6 gas pressure, then both of these density monitors close. As a result, both coils will be energized, and therefore the normally open contact of the lockout coil in series with both tripping and closing coils will be in the closed position. Then, the normally closed contacts of the SF6 alarm coil will be in the open position. Now, suppose the SF6 pressure comes down to the alarm level. Then, the pressure switch of the density monitor will change its position from closed to open. Therefore, the alarm coil associated with this density monitor will be de-energized, and the normally closed contact associated with this coil will close. If this contact is connected in series with the alarm circuit, which is not shown here in this diagram, the alarm will sound to alert us about the low SF6 gas pressure. If the SF6 gas continues to leak and crosses the lockout threshold level, then the contact of the pressure switch of the density monitor associated with SF6 lockout will change its position from closed to open. This will de-energize the lockout coil. As a result, the contact of the lockout coil connected in series with both the closing and tripping coils will move to an open condition, because these are normally open contacts. Therefore, both tripping and closing operations of the circuit breaker will be blocked.
If you found this helpful, don't forget to subscribe, like, and tap the notification bell. Got questions or want us to cover a specific topic? Leave a comment. Thank you.